Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Let me know quickly. Hello Srinath, hello Sangeeta, hello Kirtana, hello Ravina, Irtika, Salit. Welcome back everyone, welcome back. So before starting this particular session, let me just quickly give you the context, what exactly we are going to do in this session. So basically it is the second part of the chapter Ionic Equilibrium. And in this particular session, we are going to complete this particular chapter, right? So Ionic Equilibrium, we are going to complete today itself. Session duration will be approximately 3 hours or 3.5 hours, and there'll be no break in between. Let me tell you that honestly, right? I hope you guys are going to stay with me till the end of the chapter. Are you ready for that? I'm good, Furkana. Thank you. Are you ready for that, people? Let me know once in the chats quickly. Let me know once in the chats quickly. Are you ready for that? Yes. So we are almost done with some 40 to 50% of the chapter. There are certain topics remaining, right? Let's try to complete these particular topics. Perfect. All right, guys. Perfect. So let's get going then. Let's get started. First of all, the first topic which we are going to discuss in today's session, what is that going to be? That is going to be a pH of mixtures of two weak acids. Whenever you will have a mixture of two weak acids, how do we get the pH of that particular mixture which contains two weak acids basically? So let's get to know exactly how to do this sort of a topic. Have a look, people. For example, I'm taking a weak acid HA1. Let's say this is one of the weak acid which I have, right? Similarly, I've got, for example, one more weak acid, that is HA2, right? These are two weak acids which I have, right? My dear students, this weak acid HA1, since it's a weak acid, means it's a weak electrolyte. When you put it into water, it will be in equilibrium with its ions, and its ions are H positive aqueous plus A1 negative aqueous, right? Similarly, the second weak acid which we have, when you put it into water, it's going to dissociate into its ions, and its ions are going to be H positive aqueous plus A2 negative aqueous. This is something which I hope every one of you know already, right? So dear students, imagine that these two weak acids are present in the same container. Imagine that these two weak acids, they are present in the same container. So can I say, in the container, I have got a mixture of two weak acids? Absolutely, I can say that. How do you calculate the pH of a mixture containing two weak acids, right? So imagine that these two weak acids are present in the same container. This weak acid is in equilibrium with its ions. Even this weak acid, it is in equilibrium with its ions. What I need to calculate? I need to calculate the pH of the mixture that contains these two weak acids, right? Now, assume certain things. Let's assume that at time t is equal to 0, its concentration is C1. This will be 0, this will be 0, right? Let's assume degree of ionization of this weak acid is alpha 1. So I would say at equilibrium, the concentration of HA1 present in the container is going to be C1 minus C1 alpha 1, correct? The concentration of H positive from this weak acid, it is C1 alpha 1. This will be also C1 alpha 1, right? In the similar way, my dear students, let's assume that its concentration is C2. This is 0, this is 0. Let's assume the degree of ionization of this second weak acid is alpha 2. So at equilibrium, I'll be left with C2 minus C2 alpha 2. This is going to be C2 alpha 2, and this is also going to be C2 alpha 2, right? Now, my dear students, these two weak acids, they are present in the same container basically. From this weak acids, you are getting H positives in the container. From this weak acids, you are also getting H positives in the container. can you just let me know what is the total H positive ion concentration? Can you let me know what is the total H positive ion concentration coming from this acid as well as coming from this acid? So the total H positive ion concentration in the container is just going to be C1 alpha 1 plus C2 alpha 2. Correct? This is the total H positive ion concentration present in the container. Now, my dear students, if this is the total H positive ion concentration present in the container, can't you calculate pH of the final solution, which is just going to be minus log of H positive net, right? Imagine C1 value is given to you, alpha 1 is given to you. Imagine C2 is given to you, alpha 2 is given to you. If all these parameters are given to you, you can calculate the total H positive ion concentration present in the container. And once you get the total H positive ion concentration in the container, you can just multiply that with minus log. You'll be getting the pH of the resulting solution. As simple as that. Number one. Number two, my dear students. Number two. Imagine that alpha 1 and alpha 2, it is not given to us. Imagine there will be some questions in which alpha 1, alpha 2 won't be given to you. You will be given with Ka1 and you will be given with Ka2. What is this Ka1 and Ka2? Ka1 is something which I call as dissociation constant, ionization constant of this weak acid. Ka2 is something which you call as dissociation constant or ionization constant of this second weak acid. Now, in some questions, you won't be given with alpha 1, alpha 2. You will be given with Ka1, Ka2 values. Remember, directly from now onwards, you can calculate the total H positive concentration in one more way as well. It is going to be Ka1C1 plus Ka2C2 ka root. This is one more way of calculating the total H positive ion concentration present in the final solution. Right? And my dear students, whenever a question is asked related to this particular topic, in your NEET examination, they'll be always giving the stoichiometry 1:1:1 only. Similarly, 1:1:1 only. They are not going to change the stoichiometry coefficients for the NEET examination particularly. Right? So do remember there are two ways to calculate the total H positive ion concentration. One is this way, if alpha values are given to us. One is this way, if Ka1, Ka2 are given to us. Right? Either ways you can calculate. Either ways you can calculate the total H positive ion concentration in the container. Just multiply that with minus log and get the pH of the final solution. As simple as that. Right? I hope this particular point is absolutely clear to you. The important point here is, which I'm going to underline so that you can remember it, that is how do we calculate the total H positive ion concentration. And this is how you calculate exactly the total H positive ion concentration, either by this particular result or by this particular result, right? Similarly, my dear students, there can be one more scenario. There can be one more scenario. Just try to understand what exactly I'm going to say. I'm writing pH of a mixture. I'm going to write pH of a mixture containing two weak bases. pH of a mixture containing two weak bases. This can be one more question which can be asked, right? And I'm going to write it in the form of the heading, pH of the mixture containing two weak bases. Imagine that in the same container, we have got two weak bases. Imagine that in the same container, we have got two weak bases. The first weak base is, for example, B1OH. This is the first weak base. The second weak base, for example, is B2OH. This is the second weak base. Imagine both these weak bases are present in the same container. Since this is the weak base, so in the container, it is going to remain in equilibrium with its ions. And its ions are B1 positive aqueous plus OH negative aqueous. Similarly, this particular weak base in the container, it's going to remain in equilibrium with its ions. And its ions are B2 positive aqueous plus OH negative aqueous. Right? Both these weak bases, they are present in the same container. This weak base is in equilibrium with its ions. This particular weak base, it is in equilibrium with its ions. Right? Now, the same procedure which will be following. Let's assume its concentration initially is C1. This is 0. This is 0. Let's assume degree of ionization is alpha 1. So I would say at equilibrium, the concentration of this particular weak base is C1 minus C1 alpha 1. This is going to be C1 alpha 1. This is again going to be C1 alpha 1. Right? In the similar way, Let's assume that at T is equal to 0. This is C2 for example. This is 0. This is 0. Degree of ionization for example is alpha 2. So I would say at equilibrium, I'll be left with C2 minus C2 alpha 2. This is going to be C2 alpha 2. Even this is going to be C2 alpha 2, right? Now I can say, since both the weak bases, they are present in the same container. From this weak base, OH negatives are liberated in the solution. From this weak base, also OH negatives are generated in the container, in the solution. If I ask you, my dear students, what is the total net OH negative concentration present in the final resulting mixture? OH negatives coming from first base, that is C1 alpha 1. OH negatives coming from the second base, it is C2 alpha 2. So if I ask you, what is the net OH negative concentration present in the final resulting mixture? It is just going to be C1 alpha 1 plus C2 alpha 2. This is one of the way by means of which you can calculate the total OH negative concentration present in the resulting mixture. Or there is one more way. I'm not deriving the result, I'm just giving you the result. Imagine that alpha 1, alpha 2 is not given. Imagine that KB1 value and KB2 value is given to us. What is KB1? It is the ionization constant of the first weak base. KB2 is the ionization constant of the second weak base. There is one more way. It's going to be under root of KB1C1 plus KB2 and it's going to be C2, right? So these are basically the two ways by means of which you can calculate the total net OH negative ion concentration present in the resulting solution. And once you get the total OH negative ion concentration in the resulting solution, you can easily calculate POH, which stands for minus log of OH negative net concentration. And once you get POH, you can use the result pH plus POH is equal to 14 at 25 degrees centigrade. From this particular result, you can easily calculate pH. So this is the general way of solving the questions which are based on the pH of a mixture containing either two weak acids or two weak bases. I hope this is clear to everyone. Just let me know once in the chats quickly. Just let me know once in the chats quickly, every one of you. Just let me know once in the chats quickly. Yes? Perfect. All right, let's try to solve certain questions so that you can understand how these concepts are exactly used. Okay, let's try to solve certain questions. For example, this is the question. From one particular question, you'll understand the topic properly. I'm sure about that. See guys, calculate the pH of 0.1 molar formic acid, which is mixed with 0.1 molar acetic acid. So basically, you are given with two weak acids. One is your formic acid, HCOOH. One is your acetic acid, CH3COOH. So first of all, both are the weak acids. Both are the weak acids, right? Now, both these weak acids are present in the same container. So we have got a mixture of two weak acids. And few minutes back only, I told you, whenever you have got a mixture of two weak acids, right? Like formic acid and acetic acid, how they are going to undergo dissociation. HCOH will be in equilibrium with H positive plus HCO negative. Similarly, CH3COH, that will be in equilibrium with CH3CO negative plus H positive. So, as you can see, assume 40% of both the acids getting ionized. So, assume 40% of both the acids getting ionized. So, alpha 1 is 0.4, even alpha 2 is 0.4. The concentration of both these acids is same. The concentration of both these acids is same. C1 value is 0.4, even C1 value is 0.1. Even C2 value is also 0.1, right? Concentration of both these weak acids is same. Now, few minutes back only I told you, how do we get the net H positive ion concentration? So I would say the net H positive ion concentration is simply going to be C1 alpha 1 plus C2 alpha 2, right? C1 value is given, alpha 1 is given, C2 is given, alpha 2 is given. Put all the values, you'll be getting the net H positive ion concentration in the final solution. Once you get the net H positive ion concentration, you can easily calculate pH, which stands for minus log of H positive net. That's all. Isn't it simple, my dear students? Say once in the chats if this particular question you can easily solve from now onwards, right? So basically, this acid is giving the H positive ion concentration as C1 alpha 1. This particular acid is also giving the H positive ion concentration in the same container, and that will be C2 alpha 2. I would say the total H positive ion concentration is going to be C1 alpha 1 plus C2 alpha 2. Now C1, C2, alpha 1, alpha 2, it's given to us, right? You'll be getting the net H positive concentration, and eventually you'll be getting the pH of the resulting pH of the final solution. Is this clear? Is this clear to everyone? Say yes or no in the chats. Say yes or no in the chats quickly. Quickly, my dear students, quickly. Right? Let me know in the chats quickly if this is clear. Perfect. Or if you want me to solve this, I can do that too. C1 alpha 1, 0.4 into 0.01 makes it 0.04 plus C2 alpha 2, this into this. It's also going to be 0.04. So the value is 0.08, which can be written as 8 into 10 raised power minus 2, right? 8 into 10 raised power minus 2. Perfect. 8 into 10 raised power minus 2. Yeah. Now, minus log of net H positive concentration, minus log of 8 into 10 raised power minus 2. You should be able to solve this. It's going to be minus log of m into n. It's going to be log of m plus log of n, simply like this. So minus you're going to write as such. It's going to be log of 2 raised power 3 plus log of 10 raised power minus 2, log of m raised power n log m. So minus 2 comes to the front, right? Log 10 eventually is 1. Now this is minus of, this is going to be 3 log 2. 3 log 2 is 0.3, and this is going to be minus 2. So it's going to be 3 into 0.3. How much that will be? 0.9. So 2 minus 0.9 is just going to be 1.1. So 1.1 is basically going to be the pH of the final solution. 1.1 is going to be the pH of the resulting solution. I hope this is clear to everyone. Right? Right? So net H positive ion concentration you got, you just multiplied that with minus log, and you got the pH of the final resulting solution. I hope you can solve these sort of questions from now onwards. Now imagine if alpha 1, alpha 2 was not given to us. If we were given with Ka1 and Ka2 value, then how would you calculate H positive concentration net? Then it's going to be under root of Ka1 C1 plus Ka2 C2. From there you can calculate the H positive net concentration, multiply that with minus log, get the pH of the resulting solution. Yeah? Clear till here? All right. Now guys, there is one more simple topic, that is a relative strength of two weak acids. What does this exactly mean? A relative strength of two weak acids. See, imagine that you have got a weak acid in one container. You have got one more weak acid in one more container. So imagine you have got two containers. First container contains first weak acid. Second container contains second weak acid. Now, among these two weak acids, which one is comparatively strong? Among these two weak acids, which one is comparatively strong? How do we check that? How do we check that? Try to understand one thing. For example, I have got a weak acid HA1 present in the container. So this weak acid HA1 in the container, it's going to remain in equilibrium with its ions. Its ions are H positive aqueous plus A1 negative aqueous, right? I'm assuming that initially concentration of this weak acid is C1, degree of dissociation is alpha 1, and its dissociation constant is Ka1. These are the things which I'm assuming, right? Now similarly, we have got one more container that contains weak acid HA2, and this HA2 is going to remain in equilibrium, that is H positive aqueous plus A2 negative aqueous. These are going to be its ions with which it's going to be in equilibrium with. Yeah. Now same procedure. Time t is equal to 0. Let's assume its concentration is C2. Degree of ionization is alpha 2. And let's assume the ionization constant of this weak acid is Ka2, for example. Right? Use the same procedure. So initially this has to be 0. This has to be 0. Now at equilibrium, the concentration of HA1 is going to be C1 minus C1 alpha 1. This is going to be C1 alpha 1. This is also going to be C1 alpha 1. Now, this is C2, this is 0, this is 0. At equilibrium, this is going to be C2 minus C2 alpha 2. This is going to be C2 alpha 2. Even this is going to be C2 alpha 2, right? Agree till here? Now, my dear students, how many containers we have? We have got basically 2 containers, right? Let me represent it in the same manner. So this is the first container, right? Similarly, this is the second container. So we have got basically 2 containers containing 2 weak acids which are in equilibrium with their ions, right? Now, my dear students, if I ask you, what is the concentration of H positive which we are getting from this particular weak acid? I would say the concentration of H positive from weak acid number 1. That is coming out to be how much? That's coming out to be C1 alpha 1. Similarly, what is the concentration of H positive in the second container? Concentration of H positive which you are getting from this particular acid, right? In the second container, that is C2 alpha 2. Now, let me clearly tell you, when you talk about strength of an acid, strength of an acid, it is directly proportional to H positive ion concentration in the container. More the H positives in the container, more the concentration of H positives in the container, stronger is going to be the acid. As simple as that. So strength of acid, it depends on the H positive ions which you are getting from the acid. More the H positive ions you are getting from the acid, stronger is going to be the acid, right? So do remember, strength of acid, that is directly proportional to the concentration of H positive. So can I say something like this? Can I say strength of acid 1 divided by strength of acid 2 will be equal to concentration of H positive coming from acid 1 divided by concentration of H positive coming from acid 2. So what is the concentration of acid H positive coming from acid 1? C1 alpha 1, and this is C2 alpha 2. You already know it, right? Now, my dear students, again one more thing. C1. What is alpha 1 basically? How do we calculate alpha 1? Alpha 1 can be written as under root of Ka1 divided by C1. I hope you remember in the last session we have discussed. If alpha is less than 0.05, then alpha has to be under root of Ka1 divided by C1, right? Similarly, denominator C2 and alpha 2 is just going to be under root of Ka2 C2. Now, dear students, the final expression will be something like this. Under root of Ka1 C1 divided by Ka2 C2. So, my dear students, whenever you want to compare the acidic strengths of 2 weak acids, these are the 2 results by means of which you can compare the acidic strengths of the 2 weak acids. Imagine that we are given with alpha 1, alpha 2, C1, C2. Imagine that we are given with all the parameters. When you put all the parameters here in this particular equation, you'll be getting a value. Let's say the value of this particular term. Let's imagine that the value of the whole term is equal to 3. What does that mean? That means strength of acid 1 divided by strength of acid 2. That came out to be 3. What does that mean? That means acid 1 is 3 times stronger than that of acid 2. As simple as that. That's what we were supposed to compare, right? We were given 2 weak acids present in 2 different containers. We were supposed to check which weak acid is comparatively strong. We got to know the H positive coming from the first weak acid. Then we got to know the H positives coming from the second weak acid. More the H positives coming from the acid, stronger is going to be the acid. As simple as that, right? So do remember this particular scenario as well, right? So this is how you compare the strengths of 2 weak acids. Strength of acid 1 divided by strength of acid 2 is equal to C1 alpha 1 by C2 alpha 2, or under root of Ka1 C1 divided by Ka2 C2, right? I hope this is perfectly clear to everyone, right, people? So, my dear students, with this, we are basically done with the pH, right? Now, we are going to move into some different topics. We are going to discuss salt hydrolysis, we are going to discuss buffer, and we are going to discuss solubility. These are the 3 important topics which students find difficult basically. But again, I'm telling you, I'm going to start these topics exactly from the scratch itself. So, before doing the salt hydrolysis, I need to teach you one simple concept so that there will be no issues in understanding the salt hydrolysis concept. Yeah? Try to understand what I'm going to say. I'm marking the heading as a relation between a relation between Ka and Kb. A relation between Ka and Kb for a conjugate acid-base pair. For a conjugate acid-base pair. Try to understand what exactly I'm going to say. Relation between a conjugate acid-base pair. Imagine that I've got an acid Ha. Imagine that I've got a weak acid Ha. Now imagine that I'm going to introduce this weak acid into water. I'm going to introduce it into water. If it is a weak acid, that means it's a weak electrolyte. So it has to remain in equilibrium with its ions. Its ions are H positive aqueous and A negative aqueous. Right? As simple as that. Now, dear students, understand one thing. This acid, after losing H positive, it is getting converted into A negative. This particular acid, after losing H positive, it is getting converted into A negative. So I would say this acid, after losing H positive, is getting converted into A negative. So this A negative I'll be calling it as the conjugate base. The conjugate base of this particular acid. Acid, after donating H positive, it gets converted into A negative, for example. So A negative I'll be calling as the conjugate base of the acid. For example, you have got the acid Hi, right? When you put it in water, it gets converted into H positive plus I negative. So after the liberation of H positive, it got converted into I negative. So if this was the acid, then after the donation of H positive, I'll be calling this I negative as the conjugate base of the same acid. Right? I'll be calling it as the conjugate base of the same acid. I hope this is something which you already know, right? Now, my dear students, try to understand. Since I told you the acid, after the liberation of H positive, it got converted into A negative. A negative I'm calling as conjugate base of the same acid, right? So Ha and A negative. Ha and A negative. These are the conjugate acid-base pairs. These are the conjugate acid-base pairs, right? Now, since you have introduced this acid into water, since it's a weak acid, so it's remaining in equilibrium with its ions, correct? Let's assume that the ionization constant of this weak acid is, for example, Ka. Let's assume that the ionization constant of the weak acid is Ka. If the ionization constant of the weak acid is Ka, how do I write the expression of Ka? It is going to be concentration of H positive raised power 1, concentration of A negative raised power 1 divided by concentration of Ha raised power 1. This is how you are going to write the expression of Ka, right? Now, my dear students, try to understand one thing. When you introduce this acid into water, it gave away H positive and it gave A negative. This conjugate base A negative, which is liberated, which is produced, this conjugate base is further going to interact with water. Since you are introducing acid into water, so already in the container there was water, and in that water you are introducing acid. Now the acid is remaining in equilibrium with its ions. This A negative, which is the conjugate base of the same acid, the conjugate base is further going to interact with the rest of the water in the container. It is going to interact with the rest of the water in the container. Now what's going to happen? This conjugate base is going to interact with the rest of the water. Now water already has two types of ions in it, H positives and OH negatives. Can you let me know with which ion, H positive or OH negative, with which ion this A negative is going to interact? I would say this A negative will interact with H positive, right? And when A negative interacts with H positive, it's going to lead to the formation of Ha aqueous, and you'll be left with OH negative. You will be left with OH negative. Perfect. My dear students, let's assume that the ionization constant of this conjugate base, A negative, that's Kb. Kb is the ionization constant of this conjugate base A negative, which interacted with the water. Can you write the expression for Kb over here? Absolutely, you can do that. Start with the product. It is concentration of Ha raised power 1, concentration of OH negative raised power 1 divided by concentration of A negative, right? That's how you are going to write the Kb expression. You got the Ka expression, you got the Kb expression. Now, dear students, if I just want you to multiply Ka with Kb, see what you'll be getting exactly. What is the Ka value? Ka value is concentration of H positive, concentration of A negative divided by concentration of HA multiplied by Kb. Kb expression is concentration of HA multiplied by concentration of OH negative divided by concentration of A negative. Now see which all terms will get cancelled out. So I would say HA will get cancelled out. A negative will get cancelled out. So I'll be left with only concentration of H positive multiplied by concentration of OH negative. Do you remember this H positive concentration multiplied by OH negative concentration? What we used to call it? We used to call it as ionic product Kw. I hope you remember that. I hope you remember that. So I am getting one simple result over here. That is ionization constant of the weak acid multiplied by ionization constant of the conjugate base of the same weak acid. It will always be equal to ionic product of water. And if you remember, at 25 degrees centigrade, your Kw value, that is equal to 10 raised power minus 14. That's something which we have discussed already in the last session. So this is one result which I would want you guys to remember from now onwards. Right? Perfectly done. But do remember, this is the ionization constant of the weak acid. And this is the ionization constant of the conjugate base of the same weak acid. Right? If you got it exactly, can you let me know the answer of this particular thing? Just let me know in the chats. For example, I've got the weak acid CH3COH. Its ionization constant is Ka. For example, I have got one more base, NH3. Its ionization constant is Kb. Can I write Ka multiplied by Kb as Kw? Is this correct? Is this correct? Just let me know once. Is this correct? What do you think? Is this correct, my dear students? Quickly. I'm just asking you, is it correct? It's not correct, right? You know it. Ka is the ionization constant of this weak acid. And Kb has to be the ionization constant of the conjugate base of the same weak acid. Right? And if you see here, conjugate base of CH3COH will be CH3CO negative. If this is the Kb for it, then this statement makes a sense. Then this particular statement makes sense. Otherwise, it doesn't. Right? Perfect. I'm sure you can solve these sort of things from now onwards. It is just you have to remember it. Now, guys, our actual topic, that is salt hydrolysis. One of the confusing topics, right? But again, we'll be starting from the basics itself. So try to understand each and everything in detail. How do you define the salt hydrolysis? Before defining the salt hydrolysis, let me quickly show you the types of salt which we have. The types of salts which we have. Let's try to understand how many different types of salts we have. Then once you get to know how many different types of salts we have, then we can easily talk about what salt hydrolysis is all about. Right? Now, for example, if I ask you how salt gets formed, you'll directly say when acid reacts with a base, it directly leads to the formation of salt, and with that salt, you'll be getting water as well. Correct? For example, I'm taking HCl and I'm taking NaOH. HCl, when it reacts with NaOH, it will lead to the formation of NaCl. Correct? Now, which category of salt this NaCl is? Which category of salt this NaCl is? So basically, you have got Na positive, Cl negative. Na positive has come from NaOH. Cl negative has come from HCl. So, if you talk about these, this is the example of strong acid, this is the example of strong base. So I would say this NaCl, it is the salt of strong acid and strong base. It is a salt of strong acid and strong base. As simple as that. Right? For example, let's say you have got CH3COH and you are making it react with NaOH. The CH3COH, it's a weak acid. NaOH, it's a strong base. Now, when they react, what they exactly are going to give? They are going to lead to the formation of salt. Salt is going to be CH3CONA. Right? This is the salt. And with that, you'll be getting water as well. Now, tell me one thing. This is basically CH3CO negative and Na positive. We say this CH3CO negative has come from CH3COH. Na positive has come from NaOH. So can I say this is again the salt? This is the salt of weak acid and strong base. Absolutely, this is the salt of weak acid and strong base. Right, people? As simple as that. Now, for example, let's say I have got HCl and I'm making it to react with NH4OH. So what do I get as the product? I'll be getting NH4Cl as the product here. This is the salt. So it is basically NH4 positive. This is Cl negative. Can I say this NH4 positive has come from NH4OH and Cl negative has come from HCl? This is a strong acid and it's a weak base. So I must say this is the salt of strong acid and weak base. So this NH4Cl, it is the salt of strong acid and weak base. Correct? And at the end, for example, you have got CH3COOH and you are making it to react with NH4OH. This is weak acid, even this is weak acid. Sorry, even this is weak base. Acid base will make it salt and the salt is going to be CH3COONH4. So it is basically CH3CO negative, NH4 positive. So just tell me, CH3CO negative has come from CH3COH. NH4 positive has come from NH4OH. So I would say it is again the salt of weak acid and weak base. So my dear students, first of all, you should be able to distinguish the category of the salt. You should be able to distinguish the category of the salt. I'm damn sure from now onwards, you can easily distinguish which type of salt do we have. Right? Perfect. I hope you can easily distinguish from now onwards which type of salt exactly we have. Whether we have given with the salt of weak acid, strong base, weak acid, weak base, strong acid, strong base, etc. Right? If you exactly got to know how to distinguish the salts, then let's try to understand what the salt hydrolysis exactly is all about. See guys, how do you define the salt hydrolysis? First of all, the interaction of ions of salt with water to produce either acidic or alkaline solution. The entire phenomenon is called a salt hydrolysis. What does that mean? Have a look. For example, you have got a salt AB. Let's say this is the salt AB, right? This is the salt AB. It actually contains A positive and B negative. Now, for example, you are introducing this salt in water. You are introducing this salt in water. In water, already you have H positives and OH negatives. In water, you already have H positives and OH negatives. Now, there's a possibility that the ions of the salt will interact with water. Let's assume that this A positive is going to interact with water. You tell me, with which ion of water this A positive is going to interact? I would say this A positive will interact with OH negative. So it will lead to the formation of AOH, and with that, you'll be getting this particular H positive as well, right? There was one more possibility. When you introduce salt in water, I can say the N ion of salt can also interact with water. So if the N ion has to interact, with which ion of water is going to interact? It's going to interact with H positive. So it will lead to the formation of HB. And with that, you'll be getting OH negative as well. The interaction of ions of salt with water to produce either acidic or alkaline solution. The phenomenon is called as salt hydrolysis. Over here, in the first case, it is the cation of the salt which interacted with water. In the second case, it is the anion of the salt which interacted with water. Do remember, when cation of the salt interacts with the water, this hydrolysis is what you call as cationic hydrolysis. Similarly, when anion of the salt is interacting with water, this particular hydrolysis is what you call as anionic hydrolysis. So we have to discuss these two hydrolysis in detail. Cationic hydrolysis, when the cation of the salt interacts with the water. Anionic hydrolysis, when the anion of the salt interacts with the water. Right? Perfect. Do remember one more thing. One important thing. It will make everything easy for you. Just remember it directly from now on. Right? Do remember that ion of salt interacts. That ion of salt interacts with water, which has either come from weak acid or weak base. It is basically that ion of salt which has either come from weak acid or weak base. That ion of salt is going to interact with water. It will make a lot of things easy for you. Just remember it directly, right? No need to go into the detailed explanation, etc., etc. We just need this statement. We'll be using this statement and trying to solve the equations. That's more than sufficient for you, right? Now, let's try to analyze. Let's try to understand all the things. First of all, these are the different types of salts. These are the different types of salts. For example, you are taking NaNO3. Don't look at all the headings. Don't look at all the headings. Just look at NaNO3. Can I say I have got Na positive, NO3 negative? Can I say Na positive would have come from NaOH and NO3 negative would have come from HNO3? This is something which you already know. It is a strong base. This is a strong acid. So I would say the salt NaNO3, it is a salt of strong acid and strong base. As simple as that, right? Similarly, the rest of the things also you can check. The rest of the things you can also check. Yeah, the rest of the things you can also check. For example, you have got KCN. It is basically K positive, Cn negative. K positive would have come from KOH and Cn negative would have come from HCN. This is the example of strong base. This is the example of weak acid. So KCN is the example of weak acid and strong base. That's how you exactly check whether the salt is of which type. Okay. Now, one by one, we are going to discuss certain things. So first of all, we'll try to understand the salt hydrolysis of that salt, which is made up of weak acid and strong base. We are going to understand the hydrolysis of the salt of weak acid and strong base. Try to understand. First of all, the example of the salt of weak acid and strong base, that is CH3CONa. It is the perfect example of what? It is the perfect example of the salt of weak acid and strong base. Now tell me one thing. When you introduce the salt into water, it is going to lead to the formation of CH3CO negative, and with that, you'll be getting Na positive. This is understood, right? When salt is introduced in water, it will be broken down into its ions. Absolutely. Let's assume that the concentration of the salt was C, right? This was zero. This was zero initially. Now this salt, imagine it got entirely converted into its ions. So concentration of this ion is C molar. The concentration of this ion in the container is also C molar, right? Now guys, try to understand. Tell me one thing. You introduce salt into water. There are two types of ions present in the container now. One is CH3CO negative, one is Na positive. Na positive has come from NaOH. CH3CO negative has come from CH3COH. CH3COH is a weak acid. So this particular ion has come from weak acid over here. So I would say this particular ion is going to interact with water. It's going to interact with water. I told you that ion of the salt, only that is going to interact with the water, which has come from the weak acid or weak base. This particular ion has come from weak acid, right? So it is going to interact with water. So my first reaction will be the hydrolysis reaction. So what is happening in the hydrolysis reaction? I would say CH3CO negative. It is going to interact with water. And when it will interact with water, what it will lead to the formation of? The CH3CO negative will interact with the H positive of water, right? So it's going to lead to the formation of CH3COH, and with that, you'll be getting OH negative as well. So this is my first reaction which is happening, that is hydrolysis reaction, right? That's hydrolysis reaction. Now, my dear students, once this hydrolysis is done, whatever product you get in the hydrolysis reaction, that product undergoes dissociation. So second reaction is followed by dissociation. The product which is formed in the hydrolysis, right? That product undergoes dissociation in the second step. So CH3COH, since it's a weak acid, so it will undergo dissociation. It will remain in equilibrium with its ions. Its ions are CH3CO negative aqueous. With that, you'll be getting H positive aqueous as well, right? Now let me define some terminologies. The first reaction, that's hydrolysis. The second reaction, that is the dissociation reaction of the product which you get in the hydrolysis reaction. Till now, I used to write alpha, degree of ionization. But here in the hydrolysis reaction, I won't be writing alpha. I'll be writing H. H stands for degree of hydrolysis. Terminologies are different, meaning is same. Whatever alpha used to represent, same H is representing here. Alpha we used to call as degree of ionization. Here H I'll be calling as degree of hydrolysis. H I'll be calling as degree of hydrolysis, right? Degree of hydrolysis. Since the equilibrium constant of this first reaction, I'll be calling it as KH. What is KH? This is something which I'll be calling as hydrolysis constant. Hydrolysis constant. KH is something which you call as hydrolysis constant. Similarly, this is weak acid which is undergoing dissociation. So its ionization constant is, for example, Ka, right? Now, dear students, try to understand few important things which I'm going to tell you. If I ask you to write KH expression, you're going to write in the similar way as you used to write equilibrium constant. KH expression, it's going to be concentration of CH3COH raised power 1, concentration of OH negative raised power 1 divided by concentration of CH3CO negative. This is how you write KH expression. Similarly, if I ask you to write Ka expression, how exactly you're going to write? You're going to write it like this. CH3CO negative multiplied by H positive divided by concentration of CH3COOH. Perfect. Now, if I just do one thing, I'll be multiplying these two things. Let's see exactly what do we get. If I multiplied KH with Ka, if I multiply KH with Ka, what all things will get cancelled out? CH3CO negative cancelled. This term gets cancelled. So I'll be left with only H positive concentration multiplied by OH negative concentration. And you already know your H positive concentration multiplied by OH negative concentration. That's basically Kw. So I'm getting one result. KH is equal to Kw divided by Ka. This is the first question which is asked. Calculate the hydrolysis constant. Calculate the hydrolysis constant. Whenever you are supposed to calculate the hydrolysis constant of the salt, of weak acid and strong base, it's always Kw divided by Ka. Kw value at 25 degrees centigrade, you already know that's 10 raised power minus 14. And Ka will be given to us as per the question. So the first part of the question is done. KH value we calculated. Second part of the question is how do you calculate H? How do you calculate H? My dear students, how do I calculate H? What is H? H is basically alpha of the first reaction. How you used to get alpha? Alpha used to be equal to under root of K by C. So H you'll be getting under root of KH divided by C, right? So it's going to be under root of KH. KH is nothing, that's Kw divided by K multiplied by C, where C is the concentration of salt, right? Where C is the concentration of salt. This is the second question which is asked. The third question which is asked, calculate the pH of the final solution. Understand, I'm not going to derive this. I'm just going to give you the result, right? And let's try to utilize these results afterwards. Tell me, which kind of salt do we have? Salt of weak acid and strong base. We have got salt of weak acid and strong base. So base is dominating. So pH has to be 7 plus ki 7 minus. It has to be 7 plus. 7 plus half of. 7 plus half of. Which one is weak among the two? It is acid. The one which is weak, take its P value. So P of K. And at the end, it's going to be log of C, where C is the concentration of salt. This is one more question which is asked, right? So these are the three questions which can be asked from the salt hydrolysis part. These are the three questions which can be asked from the salt hydrolysis part. Either you'll be asked to calculate KH, hydrolysis constant, degree of hydrolysis, or pH, right? Well, we have got other types of salts as well, but I'm not going to derive all these for the other salts. I'm just going to give you the table. Remember that table and try to solve the questions. That's more than sufficient. Now, what that table is, let's try to make that table. Let's try to make that table. Have a look. I'm going to make one simple table. So just remember the results and try to utilize the results. Over here, I'm writing the type of the salt. Right here, I'm writing KH. This is H and this is pH, right? These are the three things which can be asked from hydrolysis part. The first is salt of weak acid and strong base. Salt of weak acid and strong base. How do I get the KH value for it? So KH is just going to be equal to KW divided by which one is weak? It is acid which is weak. So KW divided by Ka. KW divided by Ka, as you saw over here. KW divided by Ka. What is H? H is equal to under root of Kw divided by Ka multiplied by C, where C is the concentration of salt, right? How do I get the pH? It is weak acid and strong base. Base is dominating, so 7 plus half of. 7 plus half of. Which one is weak? Acid is weak. So it is P of Ka plus log of C, where C is the concentration of the salt, right? This is your first salt. Second, for example, you have got the salt of strong acid and weak base. Salt of strong acid and weak base. First is KH. KH is KW divided by, which one is weak? It is base, which is weak. So I'll be writing KB, right? So formula here is under root of H will be equal to KW divided by, it's going to be KB multiplied by C. It's going to be KB multiplied by C. Now pH, it is strong acid. So pH is going to be 7 minus half of. Which one is weak? It is base which is weak. So P of KB plus what? Plus log of C. Plus log of C, right? Now one more. That is the salt of weak acid and weak base. Salt of weak acid and weak base. So how do I write? Its KH. Its KH will be equal to KW. Since both are weak, so Ka multiplied by Kb, right? Its H is just going to be equal to under root of KW divided by Ka multiplied by Kb, right? And its pH, it's always 7 plus half of P of Ka minus P of Kb. So these are certain results which you have to remove in the salt hydrolysis case. Anything can be asked and directly formula based questions will come. Trust me on that, right? Now we will at the same time take a note of one thing. Do remember, salt of strong acid and strong base, it does not undergo hydrolysis. Salt of strong acid and strong base, it does not undergo hydrolysis. You are going to let me know the reason in the comment section afterwards. So why salt of strong acid and strong base does not undergo hydrolysis, right? You are going to let me know the answer about that. Is every single thing clear till here? Just let me know once in the chats quickly. Is every single thing clear till here? Quickly. Are all the things clear? Yeah? Perfect, guys. Perfect. Let's try to see exactly where these types of questions are asked. Oh, by the way, the table was already given to us. Why did I do all these efforts to write all these things? Anyways, let's have a look. Look at the first question. This is the first question. Calculate the degree of hydrolysis and pH of the solution. Degree of hydrolysis and pH of the solution obtained by dissolving 0.1 mole of salt in water to get 100 liters of solution. So the salt is CH3CONa. So CH3CO negative, Na positive. So it is basically CH3COONa, which can be written as CH3CO negative and Na positive. CH3CO negative has come from CH3COH and Na positive has come from NaOH. So this particular salt, it is a salt of weak acid and strong base. It is a salt of weak acid and strong base, right? So first of all, you identified the salt. Now the concentration of salt is not given to us, but what is concentration? Concentration of salt is equal to number of moles of salt divided by volume of solution in liters. So how many moles of salt we have? 0.1. What is the volume of the solution in liters? 100. So it's going to be 1 by 1000. That means 10 raised power minus 3 molar. This is the concentration of the salt. What are we supposed to calculate? Calculate the degree of hydrolysis, H. Degree of hydrolysis is equal to under root of Kw divided by Ka multiplied by C. Now, I believe all the terms are given. Kw value at 25 degrees centigrade is always 10 raised power minus 14. Ka value for acetic acid is given to us as 2 into 10 raised power minus 5. Concentration of the salt, that's 10 raised power minus 3. Can't you solve the equation? Get the degree of hydrolysis. Get the degree of hydrolysis. As simple as that. Similarly, the second part of the equation is calculate the pH of the solution. Since it's a salt of weak acid and strong base, weak acid, so it's going to be 7 plus half of P of Ka plus log of C. I believe all the terms are given to us. So it's going to be 7 plus half of P of K. P stands for minus log, right? So it's minus log of K value is given to us. 2 into 10 raised power minus 5, right? Plus log of C. C value is 10 raised power minus 3. So it is the matter of calculation only. You can easily kill it and solve it. That's all. Yeah? Is it clear? Is it clear to you quickly? So this sort of a question can be solved. I mean, can be asked. Even one more similar type of question. Just have a look. Calculate the hydrolysis constant and degree of hydrolysis for NH4Cl, whose concentration is given. Also calculate the pH. Kb is given. Again, the similar type of question. So the salt that's given to us, that's NH4Cl. So it's going to be NH4 positive, Cl negative. NH4 positive would have come from NH4OH. Cl negative has come from HCl. So this is the salt of what? It is the salt of strong acid and weak base. So first of all, you identified the salt. It is a salt of strong acid and weak base, right? Now, after identifying the salt, what do I suppose calculate? Hydrolysis constant Kh. Hydrolysis constant Kh will be equal to under root of, hydrolysis constant Kh will be equal to Kw divided by, which one is weak? It is base, right? Divided by Kb. So Kw is already equal to 10 raised power minus 14. Kb value is given to us as 1.8 into 10 raised power minus 5. Solve it, get the value of hydrolysis constant Kh. So first part is done. Second, hydrolysis constant H, which will be equal to under root of Kw divided by Kb multiplied by C. So it has to be under root of 10 raised power minus 14 divided by Kb is 1.8 into 10 raised power minus 5. And concentration of the salt should be given to us 0.1 molar. So 10 raised power minus 1. So solve it, get the answer, right? The last part of the equation, that's pH. How do you get the pH? Since it's strong acid and weak base, strong acid means pH has to be 7 minus half of. It's going to be P of Kb plus log of C. Now use the values. 7 minus half of P of Kb. P stands for minus log. Minus log of this value. Already in the last session I've told you. Minus log of this value is 4.74 plus log of C. C is the concentration of salt. Concentration of salt is 0.1 molar. That means 10 raised power minus 1. So log of 10 raised power minus 1 means it is directly going to be minus 1, right? It's directly going to be minus 1. So solve it, get the pH of the solution. That's all. So is it clear to everyone? Yeah? Is it clear? Well, I believe you can easily solve these sort of questions from now on. Gopika, we'll talk about that some other time, okay? Let's concentrate on the studies now. So again, you should be able to solve these sort of questions. Again, if you have a look, this is one more question. A 0.25 molar solution of pyridinium chloride. So salt is given, pyridinium chloride was found to have a pH of this much. What is Kb? Again, it's simple. Just identify the salt. Quickly, identify the salt. It is C5H5 NH positive Cl negative. Cl negative has come from HCl, strong acid. This has come from pyridine. Which is weak base. So it is a salt of weak base and strong acid. How do you calculate its pH? It's going to be 7 minus half of P of Kb plus log of C. Right? So pH is given to me as 2.75 is equal to 7 minus half of. P stands for what? Or let's get the P Kb value first of all. P of Kb plus log of C. C is the concentration of salt, which is 0.25. 0.25 means 25 by 100, which is 1 by 4. It can be written as 1 by 4, just to make the calculations a bit easy, right? So how exactly are you going to write it? It's going to be half of P of Kb plus log of m by n is log of m minus log of n. Log 1 is 0 minus log 4. Log 4 is 0.6. Right? Is equal. It's going to be 7 minus 2.75. How much that will be? That will be 4.25. So it's going to be P of Kb minus 0.6 is equal. How much is going to be? It's going to be 8.5, I believe. Right? So P of Kb has to be equal 9.1. Perfect. So what is P of Kb basically? P stands for minus log. Minus log of Kb is coming out to be 9.1. Perfect. It's coming out to be minus 9.1. Right? So you can write the answer like this. Log of Kb is equal to minus 9.1. Let's say the answer is given in terms like this. So Kb should be equal to 10 raised power minus 9.1. This can be the answer which can be mentioned, right? Or if you want to use the antilog, you can use the antilog as well. You can use the antilog as well, right? Perfect. Perfect, guys. Is that clear? Is that clear? Let me know once in the chat quickly. Sir, English mat karo, please. Bro, this is the English channel. English channel है ये. यहाँ पे अंग्रेजी में ही बात होती है. Quickly, people. All the things are clear? Perfect. So there are few more types of questions which can be asked from salt hydrolysis, but those questions we can only solve once we get to know, first of all, what buffers are. First, we have to understand buffer. Once we understand buffer, once we get certain results, then there can be some other questions in which buffer is related to salt hydrolysis. Those are some good questions basically, right? In which majority of the students make mistakes, right? But again, this part also will be doing from the basics itself. Now tell me once in the chats if every single thing is clear till here, quickly. Quickly. Quickly, people, everyone. All right, so let's get to know exactly what buffer solutions are. Let me show you the definition. Then I'll make you understand what these buffers exactly are. Buffer solutions, let me tell you, these are special type of solutions. These are some special type of solutions whose pH does not significantly change on adding small amount of acid or base into it. These are some special type of solutions in which pH does not significantly change upon the addition of small amount of acid or a base. So what do? They show resistance towards the change in pH. They show resistance towards the change in pH. Why they show resistance towards the change in pH? Why their pH does not significantly change on adding small amount of acid or base? You'll get the idea in some time. Why it happens? You'll get the idea, right? First, try to understand this particular definition. So what is a buffer solution? Buffer solution is the one which shows the resistance towards the change in pH. Buffer solution is the one whose pH does not significantly change upon the addition of small amount of acid or base into it, right? Now, before making you understand why exactly it happens, let me first of all tell you what are the different types of buffers. Well, we have got two types of buffers basically in our syllabus which we have to study. One is simple buffer, one is mixed buffer. Simple buffer, it is made up of a single substance. It is made up of a single substance. For example, you have got a salt of weak acid and weak base. If you take a salt of weak acid and weak base in the container, it can behave like a buffer. It will behave like a buffer. If you take a salt of weak acid and weak base, for example, you have got CH3, COONH4. This is the salt of weak acid and weak base. If you put it in a container, right, you'll find its pH won't significantly change upon the addition of small amount of acid or base, right? So it's behaving like a buffer. There are mixed buffers too. What are mixed buffers? Mixed buffers, they are the mixture of two substances basically. What is simple buffer? Simple buffer is made up of only single substance. There's a single substance which behaves like a buffer. But mixed buffers, these are made up of two substances. There'll be two substances present in the container, right? And these mixed buffers, we classify them into acidic buffer and basic buffer. And this acidic and basic buffer we have to study in detail basically, right? So let's try to understand what this acidic buffer is, what the basic buffer is, and how they exactly work. This is actually something which is in our NEET syllabus, right? Nothing apart from this can be asked. So first of all, acidic buffer, how it is made up of. Acidic buffer, it is made up of weak acid and the salt of same weak acid with a strong base. For example, you have got CH3COH. It's a weak acid, right? What the CH3CON is? It is the salt of same weak acid which it has formed with strong base, right? It is the salt of same weak acid which it has formed with strong base NaOH, right? So whenever you find weak acid and the salt of same weak acid which it has formed with a strong base in the same container, you'll be calling it as the acidic buffer. Similarly, what is the basic buffer? Basic buffer, whenever you have a weak base and the salt of same weak base which it has formed with a strong acid in the same container, you'll be calling this particular mixture as the basic buffer. So what is acidic buffer? What is basic buffer? Acidic buffer, weak acid and the salt of same weak acid with a strong base. Basic buffer, weak base and the salt of same weak base with a strong acid, right? So first of all, you need to identify, you should be able to identify which one is your acidic buffer and which one is your basic buffer, right? Now let's try to understand how these buffers exactly work. Try to understand. First of all, imagine that in the container, you have got a weak acid and this is the salt of same weak acid with a strong base. So should I be calling it as acidic buffer? Absolutely, I should be calling this as the acidic buffer. Now try to understand. CH3COH is a weak acid. If CH3COH is a weak acid, can I say it's going to remain in equilibrium with its ions, and its ions are CH3CO negative, and with that you get H positives, right? This is the weak base which is in equilibrium, for example, with the ions. Let's say its concentration is C. This is 0. This is 0. Let's say its degree of ionization is alpha. So this is C minus C alpha. This has to be C alpha. Even this has to be C alpha. This is something which we all know already. Now, in the same container, we are adding CH3COONA. We are adding CH3CONA, which is a salt. And this particular salt, it will completely get dissociated into its ions. Its ions will be CH3CO negative, and with that you'll be getting Na positive, right? In the same container, you are introducing a salt. Let's assume its concentration is C1. This is 0. This is 0. Now this is a salt. It will get 100% dissociated. So this will be 0. This will be C1. This will be C1. Now you tell me one thing. There was a concept which I discussed with you in the last session. That was common ion effect. My dear students, do you see one thing? In the same container, we have got weak electrolyte and a strong electrolyte present in the same container. Both are having one ion in common. Which effect is going to operate here? Common ion effect is going to operate. And because of common ion effect, what is going to happen? This reaction shifts in the backward direction, due to which alpha value will decrease. And that decrease in the value of alpha, is something which you call as common ion effect. Right? This is something which I'm damn sure you already know. Correct? So basically, this is something which is happening in the container. Now imagine, my dear students, you are adding some small amount of acid into it. Imagine that you're adding some small amount of acid into it. You're adding some small amount of acid into it, right? You're adding H positives. For example, just to make you understand, let's assume that you are adding 10 H positive ions. If you are adding H positives in the container, can I say strength of acid should increase? Because you are adding some extra H positives, 10 H positives in the container, for example. So acidic strength of the solution should increase, right? Or I can say pH of the solution, pH of the resulting mixture, it should decrease because you are adding 10 H positives. But what exactly happens when you are adding H positives? Already this particular reaction was in equilibrium. Right? Now when you are adding H positives, what will Le-Chatelier principle do? You are adding acid. That means you are increasing H positives. If you are increasing H positives, equilibrium will shift in such a direction which will neglect the effect of change. Equilibrium will shift in such a direction which will nullify the effect of change. I hope you remember that. Since you are adding small amount of acid into it, But at the same time, this equilibrium will shift in such a direction in which the concentration of H positive will decrease. You are adding H positives, but equilibrium will try to decrease the H positives. How equilibrium will try to decrease the H positives? When it will make the reaction to move in the backward direction. It is further making sure the reaction moves in the backward direction. And when the reaction moves in the backward direction, CH3CO negative is reacting with H positive and making again CH3COH. So concentration of H positives is decreasing. No doubt you have added 10 H positives, but understand and imagine, for example, out of those 10 H positives, 9 H positives reacted with CH3CO negative and formed CH3COH. So effectively, no doubt you have added 10 H positives, but effectively there is increase of only 1 H positive. All the 9 H positives they participated in the backward reaction, right? Effectively, there will be the effect of only 1 H positive increase. So I had expected that I'll decrease the pH. I had expected that I'll decrease the pH by adding 10 H positives. But the effect of 10 H positives is not considered here. The effect of only 1 H positive is considered here, right? So what is going to happen? What is going to happen? We were expecting, for example, the pH will decrease by 2 units by the addition of 10 H positives. But effectively, there is only increase of 1 H positive. So will the pH decrease by 2? No. For example, the pH decreases by 0.1 only. Right? So can you see this particular solution? Its pH is not significantly changing upon the addition of small amount of base into it. Right? So can you see this particular mixture, it is showing resistance towards the change in pH? Any such solution which shows resistance towards the change in pH, that's something which we call as buffer solution. So this is how this buffer exactly works. I hope you got it. Right? We were expecting the pH should decrease by 2 units by the addition of 10 H positives. But effectively, there is not the addition of 10 H positives. Effectively, there is the addition of 1 H positive only. Effectively. Right? So pH won't be decreasing by that amount which we expected. No. Right? That particular solution in which pH does not change significantly upon the addition of small amount of base or acid into it. That's something which we call as buffer. So it is working like a buffer. Yeah. So I hope you exactly got to know how this buffer exactly works. Right. Similarly, you can see the addition of base also. Right. By the addition of base, what will happen? Say by the addition of base, that means you are adding OH negatives. When you'll be adding OH negatives, so OH negatives will start reacting with H positives. Right. They'll lead to the formation of water. So H positive concentration will decrease. But equilibrium will again try to increase the H positive concentrations. Perfect. It will make sure the reaction moves in the forward direction. So basically, whatever you expect, that exactly does not happen. Okay, so in short, buffer is the one which shows resistance towards the change in pH. Perfect. Now, guys, there is one result which I would want you guys to remember directly. How do you calculate pH of the buffer? pH of the buffer. It is P of Ka plus log of concentration of salt divided by concentration of conjugate base. P of K plus log of concentration of conjugate base divided by concentration of acid, right? Or you can directly write as log of concentration of salt divided by concentration of acid, right? You can remember this particular result. I'll show you its application in some time. First of all, remember this. This is how you calculate pH of the acidic buffer. Similarly, if you have the basic buffer, how do you calculate pOH? You do not calculate pH of the basic buffer directly. You first calculate pOH of the basic buffer. pKb plus log of concentration of salt divided by concentration of base. This is how you calculate pOH. Once you get the pOH, then you can calculate pH by the formula pH plus pOH is equal to 14, right? Now I'm going to solve certain questions so that you can understand what kind of questions are asked out of this. See guys, I'll be starting with a basic question, with a complete basic question. Calculate the pH of 1 liter solution containing 0.01 molar CH3COH. So basically in the container you have got CH3COH and CH3COONA. The concentration of CH3COH, it is 0.01 molar. The concentration of CH3COONA, it is 0.02 molar. So can I say in this particular container, what do we have? We have got a weak acid and the salt of same weak acid. The salt of same weak acid with a strong base. So should I say that we have got the acidic buffer in the solution? I mean in the container? Absolutely, we have got acidic buffer. How do you calculate pH of the acidic buffer? pH of the acidic buffer is equal to P of Ka plus I'll write log of concentration of salt divided by concentration of acid. It is basically concentration of conjugate base, actual, right? Divided by concentration of acid. So it is pH is equal to P of Ka. P of this value is 4.74. You already know that. Plus log of concentration of salt. Salt concentration is 0.02 molar. Divided by acid concentration is 0.01 molar. So it's 4.74 plus it's going to be log of 2. Log of 2 is 0.3. So the value is going to be 5.04. So 5.04 is going to be the pH of the final solution. Right? Is this clear to everyone quickly? Did you exactly get to know how to tackle with these sort of questions? And this was the basic question. Now slowly you'll get to know the level of the questions. I hope this is clear. Let's try to solve few more questions. Look at this particular question, guys. Try to understand what the question says. Calculate the pH of the solution obtained on mixing 100 ml of 0.1 molar CH3COH with 100 ml of 0.1 molar NaOH. So as per this particular question is concerned, you are making CH3COH to react with NaOH, right? You're putting these two acids and base in the same container. So what is going to happen? CH3COH, when it reacts with NaOH, it leads to the formation of what? It leads to the formation of CH3CONa, and with that you'll be getting water. Try to understand. It's a good question and simple at the same time. At time t is equal to 0, if I ask you, how many millimoles of CH3COH are there in the container? See, molarity of CH3COH, volume of CH3COH, both are given. And you know, molarity multiplied by volume in ml, that gives me the millimoles. So millimoles of CH3COH will be 0.1 into 100. That means 10. So you have got 10 millimoles of CH3COH in the container initially. Now tell me how many millimoles of NaOH do we have? Molarity multiplied by volume. So we have got 10 millimoles of NaOH as well. So this has to be 0. This has to be 0. Now, my dear students, if you remember in mole concept, I have told you, whenever you are given with the amounts of all the reactants, which concept do we use? We use the concept of limiting reagent basically, right? Now we use the concept of limiting reagent. Balance the reaction first, which is already balanced. Identify the limiting reagent. 10 by 1, 10 by 1. Both are getting the same value. So both will be completely neutralized. So I'll be left with nothing of this. I'll be left with nothing of this as well. Now take 1 as the reference and get the product formed. 1 mole gives 1 mole. So from 10 millimoles, you get 10 millimoles. So from 10 millimoles, you get 10 millimoles. Now you tell me, since you introduced acid and base in the container, now you tell me after the reaction is complete, what are we left with in the container? In the container, there is no acid left. There is no base left. There is only salt and water left. In the resulting solution, finally in the container, there is salt and water left. And you know, salt and water, what they do? They'll do the salt hydrolysis, right? They'll do the salt hydrolysis. Now imagine and understand which salt this is. This is the salt of weak acid and strong base. So salt of weak acid and strong base will undergo hydrolysis, right? And how do you calculate the pH? When salt of weak acid and strong base undergoes hydrolysis, how do you calculate pH? It is 7 plus half of. It is P of Ka plus log of C, right? So it's going to be 7 plus half of P of Ka. P of Ka value is equal to 4.74 plus log of C. C is the concentration of salt. Well, I just know the millimoles of salt. So millimoles of salt divided by total volume in ml. Total volume is 200, right? So 10 millimoles of the salt divided by total volume in ml. That gives me the concentration. Now it is just a matter of calculation. And get the pH of the final solution. Did you get to know how did we deal with this particular question? So first of all, we understood at the end of the reaction what is left in the container. Accordingly, we applied the formula. Yes? Perfectly done. Perfect, guys. Let's try to solve a few more questions so that you can understand it properly. By the way, after solving this, Equation, you'll get the answer as 8.72. Let's try to solve few more. Calculate the pH of the solution obtained on mixing this and this. Okay. Now again in this question, we are making CH3COH to react with NaOH. And you know, when CH3COH reacts with NaOH, it leads to the formation of CH3CONa, and with that you'll be getting water. With that you'll be getting water. This has to be the reaction first of all, right? Now tell me initially, how many millimoles of CH3COH we have? Since we know its molarity, we know its volume. Molarity multiplied by volume in ml, it gives me the millimoles. So millimoles of CH3COH we already have. How many millimoles of NaOH do we have? Molarity multiplied by volume in ml. So 5 millimoles of NaOH we have. So this will be 0. This will be 0, right? Now again, I'll be using the concept of limiting reagent to get to know that after the reaction is done, what is left in the container. Now first of all, identify the limiting reagent. 10 by 1 is 10, 5 by 1 is 5. The one which gets the lesser value, that has to be the limiting reagent. So NaOH is the limiting reagent. So it will be completely consumed, right? Now 1 mole reacts with 1 mole. 5 millimoles would have react with 5 millimoles of it. I had started with 10 millimoles. Out of 10, 5 are reacting. So I'll be left with 5 millimoles of weak acid as well. At the end of the reaction, 5 millimoles of CH3COH will be also left. Now, 1 mole gives 1 mole. So from 5 millimoles, you'll be getting 5 millimoles. Even this will be 5 millimoles. Now, finally check it out. Finally check it out. What is left in the container? Finally check it out. Check it out. What all things are left in the container? Are we left with a base? No, it's consumed. We are left with some millimoles of weak acid, and this is the salt which is there in the container. And there is water as well. There is water as well. Now, my dear students, which salt we are left with? We are left with weak acid. Sorry, which acid we are left? We are left with weak acid. So there is weak acid in the container. There is salt as well. Which salt it is? It is the salt of weak acid which it has formed with a strong base. So can I say this weak acid and its salt with a strong base, they'll be leading to the formation of acidic buffer, right? Acidic buffer. Now at the same time, salt plus water, they can show salt hydrolysis. Whenever you'll be stuck, whenever you'll be stuck, which formula to use, whether to use the buffer formula or salt hydrolysis formula, you'll be always giving priority to buffer. You'll be giving priority to buffer. Okay? You'll be giving priority whenever there'll be confusion, right? Whether to use buffer formula or salt hydrolysis formula, you'll be always giving preference to buffer, right? So how do I calculate pH? I'll be using the buffer formula. pH will be equal to P of Ka plus log of concentration of salt divided by concentration of acid, right? P of Ka already, you know, that's 4.74 plus log of concentration of salt. Concentration of salt will be millimoles of salt divided by total volume. Total volume is 100 plus 50, 150. This is the concentration of salt divided by concentration of acid. Millimoles of acid divided by total volume. So this whole term is 1, log of 1 is 0. The final answer is 4.74. So 4.74 is the pH of the final solution, which we were supposed to calculate, right? Is it clear? Is it clear, guys? Quickly. Yes. Let me solve one more question. Look at this particular question. Say exactly how you guys are going to solve this. Calculate the pH of the solution obtained on mixing 50 ml of 0.1 molar CH3COH with 100 ml of 0.1 molar NaOH. I'm just changing the data in the questions. I'm just changing the data. Rest everything is same. So again, your CH3COH is reacting with NaOH, and it will lead to the formation of what? CH3CONa, and with that you are writing water as well. Correct? Now, initially at time t is equal to 0, how many millimoles of CH3COH we have? Molarity multiplied by volume in ml. So we have got 5 millimoles of this acid. How many millimoles of NaOH we have? We have got 10 millimoles of NaOH. So this has to be 0. Even this has to be 0. Right? Now, which one is the limiting reagent among the two? It is CH3COH. It will be completely consumed. How many millimoles of NaOH will be left? 1 mole reacts with 1 mole. So 5 millimoles will react with 5 millimoles. I had taken 10. Out of 10, 5 are reacting. So 5 will be left. So 5 millimoles of NaOH are still left in the container. Now, 1 mole gives 1 mole, so 5 millimoles are going to give 5 millimoles. Similarly, this will be 5 millimoles. Perfect. Now tell me one thing. What all things are left in the container? What all things are left in the container? You're not left with the acid. Acid is done and dusted. There is a strong base left in the container. There is a salt left in the container. There is water also formed in the container, right? Now, this and this, they will lead to the formation of salt hydrolysis. This and this, should I be calling this as basic buffer? You won't be calling it as basic buffer. No, you're writing wrong. It is not a basic buffer. Basic buffer means weak base and it's salt with strong acid. This is not weak base, it's a strong base. It's not a basic buffer, right? Do remember one thing. First, just to make sure you do all the questions correctly. Whenever you get confused whether to use salt hydrolysis formula or buffer formula, you'll be giving priority to buffer. Number one. Number two, between salt hydrolysis and strong acid, left, you'll be giving priority to strong acid. Salt hydrolysis and strong base, give priority to strong base. Okay. Now, these two, hydrolysis, and there is a strong base. This is a strong base, right? So which one to prioritize? So should I give priority to salt hydrolysis or strong base? I'll give priority to strong base. So strong base is going to decide the pH of the resulting solution. So which strong base is left in the container? NaOH. This strong base left in the container, it would have got dissociated further as Na positive plus OH negative, right? How many millimoles of NaOH are left? 5. This will be 0, this will be 0. This will be 0, this will be 5, this will be 5. So tell me the total millimoles of OH negative which are left in the container. Total millimoles of OH negative which are left in the container are 5. So if I ask you, what will be the concentration of total OH negatives present in the container? Millimoles of OH negative divided by total volume. So 1 by 30. So this is the concentration of OH negative present in the container. So calculate POH. P stands for minus log of OH, minus log of 1 by 30. Solve it, get the POH. Once you get the POH, then you can get the pH as well, which is 14 minus POH. Right? Perfect. Clear, guys? Again, these sort of questions, you can try it out with the help of this particular question. This is one more question, which is your homework question. This is not basically one question. These are two questions. These are two questions. Try them the similar way. The way I solve the question, in the similar way, you guys are going to solve them, right? You have to check basically what is left in the container. Whether you have to use the buffer formula, whether you have to use the hydrolysis formula, whether you have to give priority to strong acid, whether you have to give priority to strong base, right? So that's why I'm giving you this homework question. You guys are going to try it out. Okay? Now, guys, there is one more small topic, that is buffer capacity, which is represented by phi. How do you define the buffer capacity? How do you define the buffer capacity? It is defined as number of moles of H positive or number of moles of OH negative. Number of moles of H positive or number of moles of OH negative added per liter of buffer. Just a second. Let me write it like this. Number of moles of H positive or number of moles of OH negative added to 1 liter of buffer. Added to 1 liter of buffer divided by change in pH. This is the simple result by means of which we can calculate buffer capacity. Now you must be thinking how this particular result is to be used. I'll be giving you one question. Just a second. Just a second, guys. I'll be giving you one question on this so that you can understand what kind of question can be asked out of this. One simple question I'll give you and you will understand all these things in detail. Which question should I give you? Okay, one small question I'm giving you. The question is like this. 0.4 grams 0.4 grams of NaOH. 0.4 grams of NaOH when added to 200 ml of buffer. When added to 200 ml of buffer solution, increases the pH by 0.01. Calculate the buffer capacity. Basically, buffer capacity, it gives us the idea about the efficiency of the buffer. More the buffer capacity, lesser will be the change in pH. Right? More the buffer capacity, more is the efficiency of the buffer. More is the efficiency of the buffer. What is meant by the term more is the efficiency of the buffer? What is meant by the term more efficiency of the buffer? Quickly. What is meant by the term more efficiency of the buffer? What does buffer do? It shows resistance. More efficiency of the buffer means more resistance towards the change in pH. More resistance towards the change in pH. Right? Okay. So let's try to solve this one. Buffer capacity is equal to number of moles of H positive or OH negative added per liter of the buffer divided by change in pH. Just tell me one thing. You are adding 0.4 grams of NaOH. Can you let me know how many moles of NaOH you are adding? Mass of NaOH divided by molar mass of NaOH, right? So it's going to be 4 divided by 400, 1 by 100, 10 raised per minus 2. So these many moles of NaOH you are adding. These many moles of NaOH you are adding. So if you are adding these many moles of NaOH, can you let me know how many moles of OH negative you are adding? So basically you are adding same moles of OH negative, right? Because NaOH, it dissociates as Na positive plus OH negative. 1:1:1 stoichiometry, right? So these many moles of OH negative you are adding. But you are adding these many moles of OH negative to 200 ml of buffer. So can I say in 200 ml of buffer, we are adding 10 raised per minus 2 moles of OH negative. So in 1 ml of buffer, we are basically adding 10 raised per minus 2 divided by 200 moles of OH negative. So to 1000 ml of buffer, we'll be adding 10 raised per minus 2 divided by 200 multiplied by 1000. So it will be 5 into 10 raised per minus 2, right? So these many moles of OH negative basically we are adding. These many moles of OH negative we are adding to 1 liter of buffer, right? That's what we have to calculate. Moles of OH negative or H positive added to 1 liter of buffer. So we got to know towards 1 liter of buffer, we are adding 5 into 10 raised per minus 2 moles of OH negative divided by change in pH. Change in pH is 0.01, 10 raised per minus 2. So the buffer capacity came out to be 5. Done and dusted, right? Simple. Clear, guys? One more question I'm going to give you, and let me see if you can solve that or not. The question is 100 ml of 0.1 molar solution of KOH is added to 200 ml of buffer. Is added to 200 ml of buffer. Change what? Change the pH. Change the pH from 4.2 to 4.4. Calculate the buffer capacity phi. Give it a try. You should be able to solve this sort of equation as well. It's again simple, guys. Have a look. As per the question, you are adding KOH, whose molarity is this, volume is this, right? So if I ask you how many millimoles of KOH you are adding, molarity multiplied by volume in ml. So you are adding 10 millimoles of KOH. You are adding 10 millimoles of KOH. 10 millimoles of KOH. So if I ask you how many moles of KOH you are adding, so millimoles added divided by 1000. So it's 10 raised per minus 2. So these many moles of KOH you are adding. So if I ask you how many moles of OH negative you are adding, you'll directly say 10 raised per minus 2 moles of KOH we are adding, right? Because KOH dissociates as K positive plus OH negative, 1:1:1 stoichiometry. So these many moles of OH negative you are adding to 200 ml of buffer solution. So towards 200 ml of buffer solution, you are adding 10 raised power minus 2 moles of OH negative. So in 1 ml of buffer, you are adding 10 raised power minus 2 divided by 200 moles of OH negative. So towards 1000 ml of buffer, you are adding 10 raised power minus 2 divided by 200 multiplied by 1000. The value will be again 5 into 10 raised power minus 2. So these many moles of OH negative basically you are adding to the buffer. These many moles of OH negative you are adding to 1000 ml of buffer. You are adding to 1 liter of buffer. So calculate the buffer capacity. Number of moles of H positive or OH negative added to 1 liter of buffer. So in 1 liter of buffer, how many moles of OH negative you are adding? 5 into 10 raised power minus 2 divided by change in pH, final minus initial. It will be 0.2, right? 0.2 means 2 into 10 raised power minus 1. 2 into 10 raised power minus 1. So it's going to be 2.5 multiplied by 10 raised power minus 1. The value will be 0.25. So 0.25 is the buffer capacity of the buffer. Is this clear to everyone quickly? Is this clear to everyone quickly? Let me know once in the chats. Yeah? So my dear students, I'm sure that you can easily solve questions based on buffer from now onwards, right? Do you want me to solve this particular question, or will you be able to solve this question on your own? The question which I gave you as the homework, will you be able to solve this? Or you want my help in this? Do you want me to solve this question or not? I want everyone to say it. Okay, this is your homework question. Give it a try, right? If not, then do let me know in the Telegram. Okay. Now, there is one last topic that is left. What is that? That is solubility. This is the last topic of ionic equilibrium, right? It is again one simple topic. Now, first of all, what is solubility? What is solubility product? And what kind of questions can be asked from this one as well? It's again simple. Again, I'm telling you. How do you define the term solubility? Let me first of all tell you, the solubility, it's represented by S, right? It is represented by S, number one. Number two, the solubility is expressed in moles per liter. Now, what is solubility? As per the definition, it is defined as the maximum moles of solute which can be dissolved in a solution. The maximum moles of solute per liter that can be dissolved in a solution. Now, what does that mean? What does that mean? Let's try to understand what this solubility is. My dear students, for example, just to make you understand, for example, you have got water in this container. Just to make you understand, you have got, for example, water in this container, for example, right? Do you know between the water molecules, there are basically some vacant spaces present? Absolutely. Between the water molecules, there will be some vacant spaces present. Now, for example, you are adding some salt in it. Let's say you are adding some salt in it. You are adding some solute in it, right? Let's say you are adding NaCl into it. Now, this NaCl which goes into the water, where does it go? Where does it go? First of all, the NaCl which goes into the water, it tries to fill the spaces between the water molecules. It tries to fill the spaces between the water molecules, right? And whatever NaCl goes in the spaces, first of all, when this NaCl goes into water, it dissociates in the form of Na positive plus Cl negative. So these are basically Na positives and Cl negatives which go into the spaces between the water molecules, right? The maximum moles of solute added, the maximum moles of solute that can be dissolved in 1 liter of solution. The maximum moles of solute dissolved per liter of solution, that defines solubility. For example, if I say the solubility of the salt is 5 moles per liter, what does it mean? That means in 1 liter of solution, there are 5 moles of solute present. There are 5 moles of solute present. In 1 liter of solution, there are 5 moles of solute present, right? Perfect. If I say solubility of the salt is 10 moles per liter, what does that mean? That means in 1 liter of solution, there are 10 moles of solute present. There are 10 moles of solute present, right? I hope you got the idea of what the solubility is. Maximum moles of solute, maximum moles per liter which can be dissolved in the solution. That defines the solubility of the solution. Now, there are few things which you need to know. That salt whose solubility is greater than 0.1 molar, you call that particular salt as the soluble salt, right? That particular salt whose solubility is between 0.01 to 0.1, you call that as the slightly soluble salt. And that particular salt whose solubility is less than 0.01 molar, you call that as the sparingly soluble salt. Sparingly soluble salt, right? So based on solubility, we classify salts into 3 types. One is soluble salt, slightly soluble salt, and sparingly soluble salt. And in this particular topic, we have to deal with the sparingly soluble salts, right? We have to deal with the sparingly soluble salts. Now try to understand few things what I'm going to say. There are 2 statements which are mentioned. My dear students, a sparingly soluble salt will be considered as a weak electrolyte. A sparingly soluble salt whose solubility is less than 0.01 molar, that will be considered as a weak electrolyte, and we are always going to keep it in equilibrium with its ions. Point number 1. Point number 2, this point is important, and try to understand this particular point what I'm saying. For example, you have got a salt AB. You have got the salt AB, right? This is A positive aqueous, and this is, for example, B negative aqueous. Try to understand exactly what I'm going to say. In the saturated solution, the concentration of ions represent the solubility of a sparingly soluble salt. First of all, what is the saturated solution? Saturated solution is the one in which furthermore salt cannot be dissolved, because all the spaces between the water molecules would be occupied, right? That is the saturated solution in which all the spaces are covered between the water molecules. For example, you have got water in this container, and you are going to introduce AB solid in this water, right? Let's assume that this water in the container, let's assume there are definitely spaces in between water molecules, and these spaces can accommodate maximum of 5 moles of salt. These spaces between the water molecules, let's assume that they can accommodate maximum of 5 moles of salt, right? So for example, if I'm introducing 10 moles of AB in this container, out of 10 moles between the spaces, only 5 moles can be accommodated. And those 5 moles which are going to get accommodated between the spaces, those 5 moles will be present in the form of ions, right? Those 5 moles will be present in the form of ions. So at this point, should I say the solubility of the salt is 5 moles per liter, or should I say it is 10 moles per liter? The solubility is 10 moles per liter, right? No doubt you're introducing 10. Out of 10, 5 moles are adjusted in the spaces in the form of ions, right? The remaining 5 moles, they are going to settle at the bottom only. The remaining 5 moles will be present at the bottom only. As simple as that. Now, 5 moles per liter. 5 moles per liter. So, this much amount of salt, these 5 moles amount of salt, it will be present in the spaces in the form of ions. Now tell me, 1 mole of AB would have given 1 mole of A positive. So 5 moles would have given 5 moles of A positive. Similarly, 5 moles of B negative will be present in the solution, will be present in the spaces, right? So can I say whatever is the solubility of the salt? In this particular case, whatever is the solubility of the salt? Solubility of the salt is 5 moles per liter. Same is the concentration of ions here. Same is the concentration of ions in the solution, right? So do remember this particular thing. In a saturated solution, the concentration of ions is 5 moles per liter. That is actually the solubility here, right? So concentration of ions, they represent the solubility of sparingly soluble salt. So I had taken a sparingly soluble salt whose solubility, for example, is S. If the solubility is S, then this has to be S, this has to be S. So, and the units are going to be moles per liter. Units are going to be moles per liter only, right? So the concentration of these ions, they represent basically, what do they represent? They represent the solubility of the sparingly soluble salt. Yeah. Perfect. Is that clear? You got the idea? Let's say the solubility of the salt is 10 moles per liter. That means 10 moles of the salt will be present in the solution, that too between the spaces between the solvent molecules in the form of ions. Let me know honestly in the chats whether you got this particular concept or not. Then only I can move ahead. Then only I can move ahead. My dear students, try to understand. Try to understand one thing. Let's say you are taking a saturated solution of AB solid, right? AB solid. You are taking a saturated solution of AB solid, right? Let's assume its solubility is S moles per liter. Its solubility is S moles per liter. That means S moles of salt is present in the solution. Is present in the solution in the form of ions. Now tell me the concentration of ions. Tell me how many moles of A positive and B negative will be in the solution, in the spaces. Use the stoichiometry. 1 mole gives 1 mole. So from S moles, you'll be getting S moles. This will be also S moles. This is something that's understood, right? Perfect. My dear students, if I write the expression of equilibrium constant over here, expression of equilibrium constant will be concentration of A positive at equilibrium raised power 1, concentration of B negative at equilibrium raised power 1, divided by concentration of AB solid. Correct? Now this is a constant, this is a constant. So KEQ multiplied by AB, multiplied by concentration of AB. It's going to be concentration of A positive multiplied by concentration of B negative. And these are the concentrations at equilibrium. So basically the salt and its ions, they are present at equilibrium, right? In the saturated solution. They'll be at equilibrium basically. So these are the concentrations at equilibrium. These are the concentrations at equilibrium. Now tell me one thing. This is constant, this is constant. Multiplication of these constants makes it new constant. That is what you call as KSP. So how do you write the expression for KSP? Concentration of A positive at equilibrium, concentration of B negative at equilibrium, raised to the powers of the stoichiometric coefficients, right? Raised to the powers of the stoichiometric coefficient. This KSP is something which you call a solubility product. This is what you call as solubility product, right? This is what you call a solubility product. Perfect. This is what you call a solubility product. Now, I'm going to show you exactly how do you write the expression of solubility product for different types of salts. Let's get to know about that. Rina, there will be no break. This chapter will be ended in just half an hour more. Just be with me for half an hour, that's all. The chapter will be ended, right? Okay? So how do you write the expression for KSP? In order to write the expression of KSP, you just need the concentration of products. You do not need the concentration of reactant. Yeah? You do not need the concentration of reactant. Okay. For example, have a look. Have a look. This is a salt AB, which is in equilibrium with its ions. In the solution, this AB salt is in equilibrium with its ions. Right? AB salt is in equilibrium with its ions. Now try to understand. Do you understand why this equilibrium sign is in between? Any one of you has thought why this equilibrium sign is in between? So basically, let me make you understand this in this simpler way. Try to understand. See, this was water in the container. Let me just make you quickly understand this. Why this equilibrium size is in between. See guys, let's say this is water in the container. This water can accommodate maximum of 5 moles of salt. 5 moles of salt. I am introducing 10 moles of salt. 10 moles of AB. Out of 10 moles of AB, 5 moles will be adjusted between the spaces, and the remaining 5 moles of AB, remaining 5 moles of AB salt will be there in the container at the bottom. These are the 5 moles which are present at the bottom, and the rest of the 5 moles are present in the solution in the form of ions, right? So at the bottom you have got AB solid. In the solution there are A positives and B negatives, because whatever salt is there in the solution, that salt is in the form of ions, right? So at the bottom you have got AB solid, and in the solution you have got A positives and B negatives, right? Roaming around. Now for example, if one, or let me tell you one thing like this. If for example, one A positive and one B negative, if they interact in the solution, they will lead to the formation of AB solid. But at the same time, one more molecule of AB solid will come out from the bottom and will go into the solution in the form of ions. So these two, they'll be in equilibrium with each other. These two, basically, they'll be in equilibrium with each other. Right? So A positive, B negative, they are in the solution. AB solid is at the bottom. So by chance, if one A particle, one A positive, one B negative, if they interact, they lead to the formation of AB, and that AB will settle down. At the same time, from the bottom, AB, one of the AB will dissociate into the ions, so that the equilibrium is maintained between the two. Now, leaving this part aside, leave it aside. Now try to understand what I'm going to say. Tell me one thing. Let's assume the solubility of this salt is S moles per liter. S moles per liter is the solubility of the salt. Now, what will be the solubility of A? What will be the concentration of A positive? S moles per liter. B negative? S moles per liter. Now, if I ask you to write KSP expression is simply going to be concentration of A positive at equilibrium, that's S raised power stoichiometric coefficient. Concentration of B negative at equilibrium, that's S raised power stoichiometric coefficient. So KSP expression is going to be S square here, right? KSP expression is going to be S square here, right? KSP expression is S square. For example, you have got the salt in this format. AB2 solid, it gives A dye positive plus 2 times B negative. This is how it's going to get dissociated. Let's assume its solubility is S. This will be S. This will be 2 times S. Because 1 mole gives 2 moles. From S, you get 2S. Right? So this S, this is the concentration of A dye positive in the solution. And this 2S, it is the concentration of B negative in the solution. Try to write the expression for KSP. KSP expression is concentration of A dye positive raised power stoichiometric coefficient. Concentration of B negative raised power stoichiometric coefficient. So KSP has to be equal. Concentration of A dye positive is S. Concentration of B negative is 2 times S raised power stoichiometric coefficient. And the value comes out to be 4S cube. This is the KSP expression for this particular type of salt AB2. Right? Yeah? Perfect? I hope this is clear. And similarly, my dear students, let's try to understand this one. Let's assume that you have got one more type of salt, AB3. You have got one more type of salt, AB3. First of all, how it will undergo dissociation? It will undergo dissociation as A tri positive plus 3 times B negative. Right? That's something which you all must be doing. Now, for example, its solubility is S moles per liter. So what is the concentration of A tri positive? 1 mole gives 1 mole. From S moles, you get S moles. 1 mole gives 3 moles. From S moles, you get 3S moles. Right? So you got the concentration of these ions which will be present in the solution. Now write the expression for KSP. KSP expression will be equal. Concentration of A tri positive raised power stoichiometric coefficient. Concentration of B negative raised power stoichiometric coefficient. Right? So KSP expression has to be equal. This will be S. This will be 3 times S raised to the power 3. So it's going to be 3, 3, 9, 3, 27 S raised power 4. This is how you write the expression of KSP for this particular type of salt. Right? Yeah? Perfect, guys. I hope this particular point is clear to you. Now, for example, let's say you have got the salt of this type, AXBY. If you do not know how to dissociate a salt, let me just show you quickly how do you dissociate the salt. First of all, just crisscross these two factors. So it is going to be, first of all, let me tell you one thing. The charge present on A will be plus Y. The charge present on B will be minus 6. Just crisscross to get the charges. Now, how many A particles do we have? We have got XA particles and A is present in the form of plus Y. Similarly, how many B we have? Y, and B is present in the form of minus 6. Let's assume its solubility is X. So this has to be X times S. This has to be Y times S. I hope this is clear. Try to write the expression of KSP. KSP expression is equal to concentration of A plus Y raised to power stoichiometric coefficient X. Concentration of B minus X raised to power stoichiometric coefficient Y. So KSP expression has to be equal to A plus Y concentration is X times S whole raised power X. Concentration of B minus X is Y times S whole raised power Y. So KSP has to be equal. It's going to be X raised power X, Y raised power Y, S raised power X plus Y. So in general, this is how you write the expression for KSP. In general, this is how you write expression for KSP. Is this clear to everyone? Is this clear to everyone? Is it clear, people? I hope this particular concept is again clear to you. Now let's get to know what kind of questions can be asked out of these particular topics which I told you. Anyways, one more last example. Have a look. You have got A2B3. How do you dissociate it? A2B3. The way I told you a few minutes back. A2B3. How do you dissociate it? This 3 has to be the charge here. This 2 has to be the charge here. How many A particles you have? 2 A particles. The charge present on A is +3. How many B particles you have? 3. And the charge present on B is -2. This is how you are going to dissociate it, right? Perfect. Let's say its solubility is S. So this has to be 2 times S. This has to be 3 times S. In short, now you can write the expression for KSP. Perfect. So let's try to solve some questions so that you can understand the types of the questions which can be asked. One basic question with which I'm starting with. Right? Have a look. As per the question, you are given with MgOH whole twice. MgOH whole twice. First of all, how this MgOH whole twice will get dissociated? It will get dissociated as Mg di positive aqueous plus 2 times OH negative aqueous. This is how it's going to get dissociated, right? Now, dear students, let's assume its solubility is S. This will be also S. This will be 2 times S. What is the expression for KSP? KSP expression will be S multiplied by 2S ka square, which will be 4S cube. You need to get the solubility. Solubility in water is going to be KSP divided by 4 whole raised to the power what? Whole raised to the power 1 by 3. So what is KSP? KSP value is 3.2 into 10 raised to the power -14 divided by 4. Whole raised to the power what? Whole raised to the power 1 by 3. So this value will be 0.8. 0.8 into 10 raised to the power -14 whole raised to the power 1 by 3, which can be written as 8 multiplied by 10 raised to the power -15 whole raised to the power 1 by 3. The value is going to be 2 into 10 raised to the power -5. Since you got the solubility, whose units you are going to write in moles per liter, right? So this is the solubility of MgOH whole twice in water, which we were supposed to have, right? Perfect. It's a simple and basic question. Let's move on to one more. My dear students, first of all, do remember Hg2Cl2, how it undergoes dissociation. It's a special case. It undergoes dissociation like this. Hg2 di positive plus 2 times Cl negative. This is how it will undergo dissociation in water. This is how it will undergo dissociation in water. As per the question, KSP of the salt is given. We have to calculate solubility. Let's assume its solubility is S. This is S. This is 2 times S. So if I want to write the expression for KSP, it is concentration of Hg2, that is S raised power stoichiometric coefficient 1. This is 2S raised power 2. So it's going to be 4S cube. So S you are supposed to calculate. So S has to be equal to KSP divided by 4 whole raised power what? Whole raised power 1 by 3. So what is KSP? KSP is 10.8 into 10 raised power -23 divided by 4 whole raised power what? Whole raised power 1 by 3. Perfect. Right? So this can be 108 divided by 4. 108 divided by 4 means 27. 27 into 10 raised power -24 it will be. Whole raised power 1 by 3. Right? So it is 3 multiplied by 10 raised power -8. And it's going to be moles per liter. This is how you get the solubility here. Yeah? This is how you get the solubility. Let me show you one more question so that you can understand it properly. Okay, understand one more type of the question here. The solubility of Ag2O3 in water is this much. What is its solubility in 0.01 molar Ne2CO3? Till now, we were talking about solubility in water. Now, we have to calculate the solubility of Ag2CO3 in Na2CO3. In Na2CO3. First of all, Ag2CO3. Tell me how will it undergo dissociation? It will undergo dissociation as 2 times Ag positive, 2 times Ag positive plus CO3 di negative, right? Let's assume its solubility is S. This has to be 2S. This has to be S. Now, as per the question, the solubility of Ag2CO3 in water, that's given. So S value is given. So try to get the KSP value first. KSP value will be 4S cube. So it's going to be 4 into 10 raised power -12. S is 1 into 10 raised power -3. So it's going to be 4 into 10 raised power -12. So this is KSP which you got. This KSP which you got. Since solubility of Ag2CO3 in water is given, So by that, I calculate KSP. Now, what is its solubility in 0.01 molar Na2CO3? Now, if you put the same Ag2CO3 in Na2CO3, this Na2CO3 will get completely dissociated as 2 times Na positive plus CO3 di negative. Now, what about its concentration? Its concentration is 0.01 molar. This is 0, this is 0. It would have got dissociated completely. So, this is 0, this is 0.02, and this is 0.01 molar. Now, my dear students, in the same container, what do we have? In the same container, we have got a weak electrolyte and a strong electrolyte, and both are having one ion in common. So, which effect you are going to operate? You are going to operate common ion effect, due to which this particular reaction will shift in backward direction, due to which the solubility will decrease, and this decrease in the solubility is something which I'll be calling as common ion effect here. So, if I ask you what is the total common ion concentration is S plus 0.01. S plus 0.01. Assuming that S value is already less. Now, due to common ion effects, S value would have further suppressed, due to which S plus 0.01 makes it 0.01 molar. This is the concentration of common ion, CO3 di negative now, right? Perfect. Now, guys, KSP. How do I write the expression for KSP? It is concentration of Ag positive raised power 2 multiplied by concentration of CO3 di negative, which is equal to 4 into 10 raised power minus 12, right? So, Ag positive concentration you already know. That's 2 times S raised power 2. Perfect. Concentration of CO3 di negative, that is 0.01. So, 10 raised power minus 2 is equal to 4 into 10 raised power minus 12, right? So, it's going to be 4S square 10 raised power minus 2, and this gets cancelled. So, it's going to be 4 into 10 raised power minus 10. So, 4 cancel. S will be equal to 10 raised power minus 5. It's going to be moles per liter. Now, if I ask you what is this S? This is the solubility of same Ag2CO3, but not in water. Not in water. This is the solubility of Ag2CO3 in Na2CO3. With the help of what? With the help of common ion effect, we calculated it, right? With the help of common ion effect, we calculated it. Perfect. Okay, one more question. Calculate the solubility of silver phosphate in milligrams per milliliter. It will be a lot of calculation calculated in moles per liter on. Okay, first question in pure water. Second question in a solution that is 0.02 molar in AgNO3. So these are two questions. First of all, we have to calculate the solubility of silver phosphate, Ag3PO4. Ag3PO4. In water, how it undergoes dissociation. 3 times Ag positive aqueous plus PO4 tri-negative aqueous, right? So I'm going to solve the first question. Solubility of silver phosphate in water. Let's assume this is S. So this has to be 3S. This has to be S. Write the KSP expression. KSP expression will be this raised power 3, S raised power 1. So it's going to be 27, 27, S raised power 4. KSP value is given to us as 2.7 into 10 raised power minus 23 divided by 27 whole raised power 1 by 4, and this is equal to S basically, right? So it will be 10 raised power minus 24 raised power 1 by 4. So that's 10 raised power minus 6. So 10 raised power minus 6 moles per liter is the solubility, right? When you solve it, it's going to come out as 10 raised power minus 6, because this will be 0.1. So it will be 10 raised power minus 24 into 1 by 4, 4146. 10 raised power minus 6 is the solubility. This is the solubility of silver phosphate in water. This is the solubility of silver phosphate in water. But my dear students, when I solve the same question, if I want to calculate the solubility of silver phosphate in AgNO3, what exactly I should do? Solubility of silver phosphate in AgNO3. What exactly should I do? Ag3PO4, I'm introducing in AgNO3. Now tell me how this AgNO3 will undergo dissociation. Ag positive plus NO3 negative, right? Its concentration is 0.02 molar. Initially, this was 0, this was 0. 100% dissociation, so 0, 0.02, 0.02 molar. Now tell me one thing. Weak electrolyte, strong electrolyte, both are having one ion in common. Which effect will operate? Common ion effect. Due to which the solubility of this weak electrolyte will decrease, right? And eventually you can neglect solubility S. So what is the total common ion concentration? 3S and 0.02. So 3S plus 0.02. This is the total common ion concentration, which can be further written as only 0.02 because solubility is suppressed due to common ion effect, right? Yeah. Perfect. Now guys, try to understand one thing. Write the KSP expression again. KSP expression is going to be concentration of Ag positive raised power 3. So 0.02 raised power 3. Concentration of PO3 tri-negative raised power 1. So S raised power 1. KSP value that's given to me as 2.7 into 10 raised power minus 23 is equal. This will be, is the 0.02 only? Check it out. Yeah. This will be 0.02, matlab 2 into 10 raised power minus 2 whole raised power 3. So it's 8 into 10 raised power minus 6. 8 into 10 raised power minus 6. 8 into 10 raised power minus 6. 8 into 10 raised power minus 6 multiplied by S. So from here you can get the S value. It's 2.7 into 10 raised power minus 23 divided by 8 into 10 raised power minus 6. The answer will be again in moles per liter only. So this is the solubility of silver phosphate in what? In AgNO3. First you calculate the solubility of silver phosphate in water. Then you calculate the solubility of silver phosphate in AgNO3 with the help of what? With the help of common NFA. Yes, these lectures are enough for mains as well. Yes, these are enough for J mains as well. Okay. Perfect, guys. All clear? All clear? One question I'm giving you as the homework. Let me see if you can solve this or not. One question as the homework. What is the solubility of FeOH whole twice in a buffer with pH 6.5. KSP for FeOH whole twice is equal to 8 into 10 raised power minus 16. This is the question, which is your homework question, and do give it a try, guys. Right? So with this, your Ionic Equilibrium chapter is also done and dusted. Right? Our next chapter will be, I think first we'll do the concentration terms. We are left with concentration terms, right? We did not finish concentration terms in mole concept. So we'll be doing the concentration terms on Saturday, and Saturday 6 p.m. it will be. Concentration terms in one shot. Concentration terms, molarity of dilution, molarity of mixing, molarity of reacting, non-reacting, acid bases, molarity of ions, every single thing. Molarity of ideal solutions, non-ideal solutions. All those things will be done on Saturday at 6 p.m. Perfect? Hint for this question. You need hint for this question? So as for this particular question, okay, let me give you the hint. First of all, tell me how this FeOH whole twice will undergo dissociation. It will go undergo dissociation as Fe di positive plus 2 times OH negative. Its solubility is S, this is 2 times S. Now, we have to calculate the solubility of FeOH whole twice in a buffer whose pH is? The buffer whose pH is 6.5. If pH is 6.5, that means POH will be 7.5. If POH is 7.5, that means OH negative concentration is 10 raised power minus 7.5, right? So write the expression for KSP. KSP expression is concentration of Fe di positive, that's S, multiplied by concentration of OH negative, raised power 2. Concentration of OH negative already we got 10 raised power minus 7.5, raised power 2. So KSP has to be equal to S multiplied by 10 raised power minus 15. KSP value is given to us 8 into 10 raised power minus 16 divided by 10 raised power minus 15 is equal to S. So S value is coming out to be 8 into 10 raised power minus 1, or you can say 0.8 moles per liter. So this is the solubility. Clear? Clear? Now got it? It was supposed to be your question, but anyways. Hello, I give you one question as the homework in the buffer. You give that question a try. Okay, do let me know its answer. Perfect. Hello guys, with this our Ionic Equilibrium is also done. And again, I'm telling you on Saturday we shall be doing the concentration terms in one shot. Okay. So with this, I'll be taking a leave. You take care. God bless you all and love you all. Bye, guys.